Hello, everyone. It's my pleasure today to introduce Dr. Rupak Majumdar. Rupak is a scientific director at the Max Planck Institute for Software Systems. He received a bachelor degree from IIT Kanpur and a PhD degree from University of California, Berkeley. His research interests are in the verification and control of reactive, real-time, hybrid, and probabilistic systems, software verification and programming languages, logic, and automata theory. Rupak received plenty of awards. Let me cite a few ones. He got the President's Gold Medal from IIT Kanpur, the Chua Award from Berkeley, an NSF Award, a Sloan Foundation Fellowship, an ERC Award, and plenty of Best Paper Awards. So Rupak, we are really grateful and happy to have you today for our last plenary. And without further ado, I leave you the floor.
Thank you, Raphael. Let me try to share my screen and you can tell me whether you can see everything. Okay, I assume you can see my screen, right?
Yes.
Okay. So thank you for inviting me to give this talk. And it's indeed an honor for me because I've been part of the hybrid systems community for quite a while now. And today I want to talk about some work that we have been doing over the past few years on formal methods in the domain of robot programming. Now, I assume that someone will be monitoring the chat. Please feel free to put your questions there or just interrupt me. I'm happy to take questions as we go along. Okay. So the problem that we want to look at is how can we design and implement a high confidence and safe programming stack for large-scale autonomous robotic applications. Now, this is a rather long-standing challenge in many different communities. And in fact, there is this very influential paper by Tomás Lozano Pérez from 1983, where he claims that one of the great challenges in robotics is to provide programming abstractions that allow the versatility of robots to be exploited easily. And he ends his paper by stating that we do not have an understanding of the basic issues in robot programming. And what I would say is that even after 40 years, we still do not have adequate understanding of programming and reasoning support for these autonomous robotic systems. But what I would like to convince you in this talk is that over these years, we did make sufficient advances towards this grand challenge. So even though we haven't solved this problem entirely, we have made considerable progress. Okay. And by the nature of these talks, I shall provide a rather biased view that will feature the work of my group. But of course, there's a very large community that's working on all of these problems. Okay. And just to show you the kind of examples that we can now verify, let me just give you a couple of examples of some simple robot coordination protocols that we have implemented in the lab. So here, essentially, there's a cart that's kind of carrying blocks of different color to different robots. And as a robotics example, this is not particularly exciting. But what is exciting to me is that this entire code is actually formally verified.
But people are asking whether you could enlarge your screen because it's relatively small.
So let me try. This is, I think, is this any better?
Didn't change for me. For me, it's relatively okay, but I saw some people complaining.
Let me stop the sharing and try one more time.
Okay, absolutely no big deal.
Does this work any better?
Much better.
Yes.
Thanks.
Okay, so here's a second example of, again, a very simple coordination where two robots kind of meet somewhere in the middle and transfer a certain block from one cart to another one. Okay. And again, in terms of concurrent robotics, these are not very complicated examples, but considerable work needs to be done in order to verify these simple coordination protocols. Now, before we go any further, I want to mention that this problem of understanding and providing a basis for formal foundation for robot programming is an extremely interdisciplinary topic, in the sense that we need to put together many different ideas from many different disciplines, from continuous systems theory or control theory, to computer science and discrete systems theory, ideas such as automata and logics. As you will see, we also look at programming abstractions and concurrency theory. And finally, I will give you some examples of software engineering and human-robot interaction that kind of comes together in making progress on this problem. So essentially, this is a rather interdisciplinary topic, and I apologize in advance if I lose some of you in some parts of the talk. It's really a struggle for me as well in trying to understand all of these things and how they come together. Now, when we talk about formal foundations, essentially we shall look at three different things in this talk. We shall look at reasoning about dynamics, reasoning about coordination, and to a lesser extent, reasoning about resources. And when I say reasoning, I will take a computational lens. Our goal is to provide an algorithmic framework for the design and analysis of these systems. Now, when we talk about formal foundations, we shall essentially look at the problem at many different levels. So at the lowest level, we shall look at the control of dynamics. And here, the problem is that we have a combination of discrete and continuous dynamics, perhaps in the presence of uncertainties. And we shall talk about abstraction and automatic synthesis of controllers. At the next level, at the coordination level, we shall look at more discrete problems, and we shall try to understand how we can formally reason about coordination, about message passing concurrency, but not just concurrency in isolation, but concurrency interleaved with continuous dynamics. Now, when we go further up, we shall look at multi-agent systems. And these systems will not just work in a vacuum. We shall look at software engineering and systems design issues such as provisioning, scheduling, and so on. And finally, if time permits, we shall very quickly look at certain user interaction issues and how end users can use these systems in a more effective way. So most of my talk will actually focus on the bottom two levels, mostly because we have made more progress at these two levels than the other ones. But I will give you a very brief introduction to what we have been doing at the other levels. And I shall structure the talk in terms of 4 projects that we have been doing in my group for the last few years. Mascot is an automatic controller synthesis tool. PGCD is a programming framework for concurrent robots. AntLab is a task assignment and planning system for robots. And LittleTalk is an end-user programming by example system. Okay, so let's start at the lowest level. I shall talk about automatic ways of designing controllers in the presence of continuous and discrete dynamics. Now, the controller synthesis problem is probably familiar to many of you. So you're given a model that is, let us say, a continuous state, continuous time dynamical system given by a differential inclusion. And there is a nominal or unperturbed dynamics, but we also assume that there is a bounded external perturbation. So we have some state space. Let us say it's a compact state space. You have a certain point, and under the effect of the external disturbance, the system essentially gives rise to a set of trajectories. And what we'd like to design is a controller that takes a state and produces a control input to this dynamical system, such that the trajectories of the system under the influence of the controller satisfies a certain specification, which is usually in our context given by a temporal logic over the sequence of states. And our goal is to find a controller domain, or at least a good approximation to this controller domain, such that from every state in this controller domain, if you apply this controller, then you ensure that every possible trajectory, even under this bounded external perturbation, will satisfy the specification. So here's a very simple example. This is a very common case where you want to design a controller that reaches some target, these green states, and avoids certain obstacles along the way. So the goal is to reach the target, but make sure that you don't bump into the obstacles. And again, you can, the goal is to find a controller such that the dynamics that you get under the controller, even under the disturbance, will eventually reach the target, and it will never hit the obstacles. And our goal is to, again, find the set of states from which such a controller exists. And another very canonical example is safety, where again, you're given a dynamics, and the goal is to come up with a controller such that the trajectories always remain outside some set of bad states. And in general, we can look at any omega regular specification or things given in linear temporal logic, if you're familiar with such logics. Now, the core technique that we use is by now quite familiar in the community. This is something called abstraction-based control design. And this is something that came out, I would say, from the HSCC community, from the intersection between computer science and control theorists about 15 to 20 years ago. And by now, there are some excellent textbooks, by Paulo, by Kalin, by Shayan, that essentially talk about abstraction and control design in various ways. So ABCD starts with the continuous state dynamical system. In general, it can be both continuous time or discrete time. Here, I've just given a discrete time description of the system. And what ABCD does is that it first computes an over-approximation of the dynamical system on a finite state space. So the simplest way of thinking about this abstraction, this finite state space, is that you put a grid on your continuous state space. And then a finite, your finite state space is given by the cells that make up this grid. And then through a process of abstraction, what we do is that for every center point of every grid, that is for every state in my finite state space, I construct an over-approximation of the underlying dynamics. So in this picture, if you start with any one of these dots and you follow the arrows, what we can say is that if the underlying continuous state system takes one step in its dynamics, then under the effect of the disturbance, the possible states would be any one of these discrete cells that these arrows point to. Okay? So it's an over-approximation of the possible states that you could visit in one step of the underlying dynamics. And this abstraction is characterized by a parameter that says how fine your discretization is. Now, it turns out that there is a different way of thinking about this abstraction. And this is something that is called a two-player game. It's a two-player game between the controller and the disturbance. And you should think of it in this way, right? So the states of this game are the discrete abstract states that we have computed in this abstraction. And from any one of these states, the controller can decide to play any one of its control actions. We shall also discretize the control space in the same way that we do the state space. And then an adversarial player, the disturbance, essentially resolves the disturbance and figures out which new state the game ends up in. And now it turns out that the reason we go to these two-player games is because there's a lot of theory from the world of reactive synthesis and automata theory that tells us how to compute strategies that win against omega regular specifications on discrete two-player games. So essentially what we can do is that we can now apply these algorithms, and we can essentially find a winning domain of the controller on this discrete abstraction. And what is also nice is that you can take this winning domain and you can essentially refine it back to the original system. So for example, I have shown on the left-hand side a winning domain that is given on the abstraction, but that directly defines a winning region on the original system. And if there is a certain relationship that holds between the original system and the abstraction, called a feedback refinement relation, then you can show that this entire loop is sound, in the sense that if you find a controller and do this refinement, then what you get is an actual controller that ensures that every trajectory of your original system will satisfy the specification. So by now, also there are some very nice and robust tools available to do ABCD. Scott's from TU Munich, I guess now from the University of Colorado is one, pFaces is another one, and Mascot is the version of the tool that we have built at MPI. Now, of course, while the basic theory of ABCD is now quite well understood, there are a number of directions of further research that the community has been looking at for the last several years. And some of these have to do with scalability. So as you can imagine, the state space in this abstraction grows exponentially with the dimension of your underlying system. So there's, of course, several different directions that we try to cut down the state space and make sure that these algorithms terminate. And here, let me again point out this work, this excellent work by the pFaces team, Mohammed Khalid and Majid Zamani, who have essentially scaled this technique incredibly through the use of GPUs and distributed computing platforms. I shall talk, so we have also looked at multi-layer methods, where instead of computing one abstraction all the way through, we look at multi-grained abstractions that refine the abstraction depending on the need of the underlying algorithm. We have also started looking at compositional techniques using assumed guaranteed decompositions of the reactive synthesis problem. Now, there are also different directions in expressivity, such as the ability to handle stochastic models, the ability to handle output feedback control or partial observation techniques, and also just to understand the relationship between, in general, supervisory control of discrete event systems and the more continuous versions and reactive synthesis. So for want of time, I'm just going to focus on two of these directions. And again, I will focus on some work that we have done in our group. Of course, there are several other people who have been doing work in this space. For example, Antoine Girard and Nejmi Otze have work in the multi-layer techniques. And I think several other people, including Majid and his students, as well as Sam Coogan and his students, and Murat, have excellent work on stochastic models. So this is really a thriving community, but let me focus on the couple of things that we have done in the last few years. So the first direction is this multi-layered ABCD. And the problem that it tackles is the trade-off between precision and complexity in abstraction-based control design. As you can imagine, you can start with a rather coarse abstraction of the state space. And then computations will be fast because there are few states, and you can run this abstraction and reactive synthesis algorithms fast. But this is not going to be very precise, because let us say we take this system where you have a target and you have some obstacles and the robot has to get to the target while not bumping into the obstacles. Well, if your abstraction is too coarse, then the robot may not realize that it can go through the middle of these two obstacles, and therefore the entire right-hand side of the state space would not be winning. On the other hand, you can, of course, make a much more precise abstraction and find a much larger control domain. But the cost that you pay is that you have to now run this ABCD on a much larger state space, so it will take a lot of time. So what these multi-layered algorithms do is that they essentially maintain several different abstractions at the same time. So you start off by taking the most coarse abstraction of your state space, and then you try to compute this two-player game and do reactive synthesis at the coarsest level. So this will give you some control domain. But for places where you cannot win, you compute somewhat more refined abstraction of those states. And in fact, you can do it lazily as you compute the iterations of your underlying reactive synthesis algorithm. So what you end up doing is that you maintain a sequence of approximations of the state space, and you maintain, by solving these reactive synthesis games, a sequence of winning domains for the underlying problem. And eventually you can put them all together to get the winning domain. And ideally what you do in this way is not pay the price of doing the finest abstraction all over the state space, but doing their finer abstractions only when they are necessary. And just to show you how this works, consider again a robot that has to get to this orange state on the right-hand side while avoiding the gray obstacles. So here you see that an implementation of the algorithm works on the more coarser version of the state space, which is shown using green here, and only computes finer abstractions in places that are near the obstacles or near the target in order to get a much more refined controller in those regions. But because you're computing coarser abstractions through most of the state space, your algorithm can scale much better. So let me talk a little bit about some very recent work that we have been doing in applying the same ideas to stochastic models. So here again, the problem is more or less as before. So you're given a dynamical system, which is continuous state and either continuous or discrete time. And you're now given a perturbation that is stochastic. And again, our goal is to find a controller that looks at the state and produces an input. And we are given a specification, which is again a linear temporal logic formula over states. And our goal is to now find a tight bound on the satisfaction probability of the specification. So since the system is probabilistic, we cannot guarantee all the time that a particular specification will always hold on all trajectories. But we can ask, for example, that can we find a controller such that the specification holds almost surely? Or we can ask, can we find all those places from which the controller ensures that the specification holds with probability greater than, let's say, 90%. Now, the way we handle this problem is that we essentially look at the special case of almost sure satisfaction. So what we do is that we find a controller that finds we find a controller domain from which there is a controller that ensures that the system satisfies the specification with probability 1. And then we essentially find, then we run a value iteration like algorithm to compute a probability that we can reach the set of states from which there is a controller that satisfies the specification with probability 1. Here, the specification is given as a Bucci property, but that is not so important. We can do it again for any omega regular specification. So it turns out that there are existing methods to do this kind of reachability computation by iteration. So what we'll focus on is really computing the controller region from which there is a controller that satisfies the specification with probability 1. And essentially, we can show that, if you compute this region and then do a reachability analysis, what you get is a lower bound on the probability of satisfaction of this formula. Okay. And again, what we can do is we can take the basic ABCD algorithm and essentially massage it to deal with the stochastic case as well. And the way we do this is that instead of maintaining just one abstraction as before, which was the over approximation of the dynamics, we now need to maintain two different abstractions. One, which is an over approximation of the dynamics, and the other is an under approximation of the dynamics. And there is a technical reason why you need both of them, because the way probabilities work. Okay. And now what happens is that once you have these two abstractions, you can again go to a class of games for which we know how to solve omega regular objectives. But this time, the game that you get is not a 2-player game as before. You get what is called a 2.5-player game. So these games have been studied in the automata theory literature for some time now. And the idea of a 2.5-player game is that you have two adversaries as before, the controller and the disturbance. But in addition, you also have nodes that are random. So in that sense, 2.5-player games generalize Markov decision processes to the competitive setting, where you have the controller, you have the disturbance, and you also have a probabilistic player that decides where to go next based on a probability distribution. On the other hand, given a 2.5-player game, by now it is kind of well understood how to symbolically solve for omega regular specifications. And so this is essentially what we do. So the stochastic version of ABCD starts with a discrete time continuous state probabilistic system. It computes finite abstractions, both an over approximation and an under approximation of the underlying dynamics. These two together define a 2.5-player game on which we solve a reactive synthesis algorithm. And then again, we can show that we can take this synthesized controller and we can refine it back on the original state space. And this refinement happens pretty much in the same way as we did previously. So this tool mascot that we have developed is it was developed mainly by my student Kaushik Malik, and this can now solve these kinds of stochastic control problems and quite large ones. So here's a very simple example. So the goal here is to take a Dubin's vehicle and sort of control it so that it reaches in between, it travels between a kitchen and an office many times. And there's an environment that controls a door in the middle, and the door can be open or closed. And there is some stochastic assumption on how often the door is open. So the abstract state space here is about 1.5 million states, and we can solve this kind of problem in about half an hour. Okay, so essentially what I wanted to get across is that this idea of abstraction-based control design is a rather general idea of computing correct by construction controllers for omega regular specifications. For systems that may be nonlinear, may have many other features such as output feedback, such as stochastic transition relations, and so on. And of course, the problem is very much open. There are many problems, both in terms of scalability and in terms of expressiveness, that still need to be worked on. But let me move at this point to the next level in our hierarchy. So far we talked about a single system and the problem of designing controllers for that system. The next project that I shall talk about, PGCD, is essentially a programming model which essentially, with a verification framework that reasons about geometry, concurrency, and dynamics at the same time. So the way to think about this is that we're now taking a slightly different perspective. the dynamics that we controlled and designed in the last section of the talk essentially becomes abstract motion primitives in a PGCD program. And we take a perspective where we go from single components to multi-agent systems. So we have different robots that are working concurrently. And we focus in PGCD on the interaction between dynamics and communication. And because these robots are working in the same geometric space, there is a very basic invariant that they do not collide into each other. Right? So that's how the geometry, concurrency, and the dynamics come into play. Now, in principle, I guess one could say that, well, I take a rather high-level specification and automatically synthesize PGCD programs. We don't yet know how to do this scalably, so we take a verification perspective. In that, we shall assume that the user writes these PGCD programs, and our goal will be to reason or verify them to make sure that they're correct. And just to go back to the handover example that we saw in the video. So you see the handover shows this connection between motion. So these two carts kind of moved towards each other. And then they coordinated, they stopped next to each other, and then the arm came and picked up this object. And once the arm was done with picking up the objects, they went back to moving away from each other. So essentially, the run of this kind of handover program and many other programs where several robots are interacting have the following form over time. They send each other messages for coordination. And moreover, between the messages, they execute these motion primitives that cause global time to progress. You can think of these motion primitives as a dynamic controller that you may or may not have designed using abstraction-based control design. But then now there is an additional aspect of making sure that these messages and synchronization happens in the right way. So in our model, we assume that messaging is synchronous and reliable, and it takes zero time, as does any other computation. The only way time can progress is when these motion primitives are executed. And because we are looking at multiple robots, each of these robots have essentially a coupled control dynamics so that the dynamics of the cart can be affected by the arm that is sitting on it. And the difficulty in the verification problem here is to deal with motion alternating with these messages. So the unit of software in PGCD is a process, and a process has two aspects. It has the physical aspect of the robot, and it has the software. Now, the physical aspect essentially talks about the physical state that's maintained by this robot. For example, the position and the velocity of this cart, as well as its mass, as well as the mass of an object that is sitting on it. So that's the physical state, and the physical state can be internal, which is the mass of this carrier or the position and velocity of this carrier, or it can also be external in the sense that maybe there is some thing that's on top of this cart, so that that mass will affect the dynamics of this cart. In addition, there's a communication interface that allows it to send and receive synchronous messages, and the underlying dynamic controllers are organized into a set of motion primitives. So the code that runs on this component will orchestrate the message and the motion. But in addition, we also carry around the geometry of the robot, and this is a resource that we track in our verification. And the geometry will essentially be used to make sure that two robots do not collide in geometric space. Now, PGCD takes a rather abstract view of the underlying controlled dynamics. And essentially, this is in the classical program analysis or program verification perspective, where we think of each of these motion primitives as summarized by their precondition and postcondition. So under what states can this motion primitive be executed, and what happens after it has executed. But in addition, it also carries around an assumption on the environment. An assumption on the physical state variables of the environment that affect this controller. And it also gives a guarantee on what the external world can rely upon when this particular motion primitive is being executed. And the footprint and the duration, so the footprint carries around the geometric space required for this motion. And the duration is needed because at some point we want to reason about the interaction between motion primitives and messages. Okay. And just to give an example, so here is, on the left, you see a rather simple depiction of the protocol for the handover. And you can imagine that, the arm that is sitting on that carrier executes some code where it's some kind of a while loop where it receives messages from the cart. And depending on the message received, it could apply certain motion primitives, right? So it can either idle, or it can apply a grip operation to pick up an object, or it can move to a particular point, and so on. Now, so the unit is one of these, these physical robots as well as the code on top. And of course, PGCD has a notion of composition. And the composition is a little more complicated than usual composition in a process algebra, because a composition here has to relate not just the code and the messages, but also the physical variables. So if you take a cart and you compose it with an arm, the composition process is actually a physical coupling of these things. And this would mean that certain external state physical variables of one of the systems would be bound to certain internal physical variables of the other system. So for example, if you put an arm on a cart, then the cart's external mass will now be bound to the mass of the arm. There is another slight complication, because you see the position or the reference frame of the arm is now relative to that of the cart. So that, when the arm wants to go to a certain position X, Y, and Z, this has to be transferred based on where the cart is, and replaced, and it has to be transformed to world coordinates by understanding the sequence of frame shifts that happen between the components. Okay. But for the purposes of this talk, we can essentially ignore these slight variations. You can think of it as a way of composing two systems to get another PGCD process, right? Which is a composition of the two. Okay, so what can go wrong in such a system? Well, the first thing that can go wrong is that, well, you have the two components, but the motion primitives cannot be jointly executed. And a simple example of this is that imagine that you have this cart and an arm, but maybe when the cart is, when the arm is in a certain configuration, then the cart cannot move very fast because it can topple over. On the other hand, if the arm was in a different configuration, let us say folded, then maybe the cart can move fast. The second kind of error is error in communication. What can happen is that, well, if you have message passing concurrency, you can get into a deadlock, you can send a message that nobody is willing to receive, or you may be waiting for a message while the other person is trying to execute a motion primitive. Now in this world, time is a great synchronizer. Just because you are waiting for a message doesn't mean that time will stop for you when I try to execute a motion primitive. So quite a lot of the complexity of verification is to make sure that motion and dynamics play well together. Sorry, communication and dynamics play well together. And the third thing that can go wrong is that, well, two components can collide in space. Let me give you a so before we do anything, one could imagine that you can take one of these PGCD programs and you can just apply model checking to it, because you can build the product state space as a large hybrid automaton, and then you can encode the properties as invariants, and then you can see, then you can run a model checker to see if this works, if the property holds. Unfortunately, as you very well know, may be aware of, such a thing does not scale very well because the state space explodes very quickly. So instead, what we have done is that we have explored compositional techniques, which essentially explore a scalability, expressivity, and annotation trade-off. Okay, so we will not be able to verify every possible program. On the other hand, we will scale to a number of interesting programs. And of course, we shall require some help from the user in being able to verify certain large systems. But hopefully that annotation burden would not be so big. Let me stop quickly and look at these questions. So Manuel asks, what is the under approximation in the case of stochastic systems? This requires a little more detail than I would like to take, but Manuel, let me just take this question offline and talk to you about this after the talk. And Basil asks this question about errors introduced by a motor partially failing. That's a very good question. At this point, we do not have a good way of understanding faults and failure recovery, but this is one of the directions that we would like to work on. At this point, we just assume there are no faults, which is a rather stringent assumption if you work with these robotic systems in the lab. On the other hand, we had to start somewhere, and this seems to be an interesting place to start. Okay. So Rong asks, are the motion primitives atomic in motion planning? Well, they're not quite atomic, but we assume that the pre-post assume guarantee and the duration kind of give you a lot of information about them. Now, you have already pointed out something that I swept under the rugs. We also distinguish between motion primitives that cannot be interrupted and primitives that can be interrupted or preempted. And in fact, the distinction between these two kinds of motions comes up when we do the reasoning about the interaction between message passing and the dynamics. So in our model, we essentially ensured that at any point globally in the system, there's at most one non-interruptible motion primitive, and everything else is interruptible, so that when that non-interruptible motion primitive finishes, it sends a message and synchronizes with everybody else. Okay, I hope it answers at least partially your question. Okay, so let me point out how we handle this in a compositional way. So first, let's look at dynamics. So as I said before, we model motion primitives through these assumptions and guarantees, as well as footprints. And what we do is that in order to check compatibility between two motion primitives, we essentially have an assume guarantee rule that ensures that if you have two jointly executing motion primitives, that the guarantee of one is a superset of the assumption of the other, and conversely. Okay. In other words, you can put these two motions together and make sure that they're jointly executable, that there is a joint trajectory that is possible in the system. In addition, the compatibility check also makes sure that the footprints are disjoint, and this ensures there is no collision among the systems, and also that the duration of the two motion primitives is compatible with communication. And this comes back to Rong's question about interruptibility. And the theorem that we can show is that if you do this compatibility check using this assume guarantee proof rule, then you imply that there is a collision-free joint trajectory of the underlying system. So this, in some sense, takes care of the dynamics and also the geometry. Let me move on to talking about how we deal with communication problems. Right? So these are things like deadlock and orphan messages, but also the interaction between motion and messages. And in order to do this, we take this idea from programming languages and concurrency theory, which takes a type-based view of the problem. So this is this idea of multi-party session types introduced maybe already around 15 years ago by Kohei Honda, Nobuko Yoshida, and many others. And the idea of multi-party session types is the following, right? So you have some concurrent system that's passing messages to each other, and you would like to make sure that they're correct. So the way you specify what is correct is called a global type. So this is the specification of all the allowed message exchanges in the system. And this is something that you expect that the designer of the system will write for you. Now, given such a global type, multi-party session types define a certain syntactic projection operator that takes these global types and projects them down to local types. And each local type essentially is the set of message exchanges by a single process. So it is the view of a single process on what is going on in the entire system. And the soundness theorem of multi-party session types says that if a system is projectable, if a global type can be projected onto each of its components, and then there is a subtyping that each program or each process satisfies the type given by this local type, then the entire system is communication safe. So multi-party session types essentially hit a sweet spot between expressiveness, annotation burden, and complexity. So many of these projection operations are rather simple and syntactic. So at the cost of writing down these global types for the entire system, you can essentially take this global model checking problem and break it down into type checking problems on each component. So I will skip the example. So what we did was that we extended the theory of multi-party session types to motion session types. And here, the global specification now talks about the allowed message exchanges, as well as the allowed joint motion primitives between message exchanges. So when you do this, you can again define a certain projection, and you can show a soundness theorem that says that when a system is when a global type is projectable onto each process, then the system is communication safe. But technically, the motion session types become a lot more complicated because, as I said before, time is a global synchronizer. So if one system is ready to execute its motion primitive and another one is waiting for a message, then this is an error. And this is something that the type system has to track, and it requires a certain causality analysis on the global types that you have to do. Okay, very quickly, and I don't expect you to read this entire thing, so one can take our handover example and write down a global specification in this motion session types. And this global specification essentially tells us the sequence of synchronization and motion that happens in the system. We can do the syntactic projection, let us say, to the ARM process and see what messages and what motions that this particular process is supposed to do and in what order. And once you have this projection, you can essentially see that the projected type looks very similar to the code that I showed at the beginning. And essentially, you can do a type check with a certain subtyping to make sure that the ARM satisfies this type. And once you do this analysis for each process, the cart, the ARM, and the carrier, you have been able to show that the entire system is correct. So we have implemented this entire framework, this PGCD programs, a motion primitive library with annotations. We do this session types projection. We do these refinement and motion compatibility checks. And we now have a compiler from these PGCD programs all the way down to systems that run on top of ROS. And just as an example, this is one of the video examples that I showed in the beginning. So just to show you the complexity of this coordination, there are 5 participants, including some robot arms that we bought and others that we built in the lab. The coordination had 16 messages and 53 different kinds of motion primitives. And essentially, the whole point here is to show that the annotation burden is not very high. So you remember that we have to give these specifications of the motion primitives as well as write down the global type. And we can actually automatically verify, on top of an SMT-based verification condition generator and verifier. And most of the time goes into the joint compatibility checks. And part of it is because the geometric reasoning requires nonlinear arithmetic, And this is somewhere that the SMT solver really needs to do some work. But the typing and the syntactic checks are really minimal in the whole verification process. Okay. So I'm gonna move up to the last part of the talk where I'll very briefly talk about the rest of the projects, but let me stop and take a couple of questions now. So Paritosh asks, yes, so the scalability expressivity annotation trade-off is essentially that instead of doing a completely automatic model checking on the entire state space, what we are doing is that we are asking for these type annotations, and we are also asking for these annotations of pre-post assumes and guarantees for these motion primitives. Now, this is not always so easy to give, but this is really the trade-off, right? So we are scaling to somewhat complicated examples because we are asking the programmer for help with these motion primitives and global types. And we are also essentially using session types, which are sound but not necessarily complete. Right? So it is possible that the session types will reject a program which is actually correct. Okay. So Manuel asks, why not use timed automata for the planning of messages and actions? Well, we went for the type view just because we wanted to have a very compositional way of looking at the system, and the types were, came with a compositionality result. Whereas for timed automata, I think that we would have to somehow come up with some way of doing this projection on timed automata. It looks rather interesting. I don't know offhand how easily we would be able to do this. So this question about controller synthesis using types, we haven't really thought about it, in the sense that it seems that if you completely merge, so maybe the short answer is that we haven't thought about it, right? But maybe there is a way of doing it while maintaining scalability. Okay. And this question of how ABCD deals with continuous time, well, I kind of didn't talk about it here, but just as we do discretization of the state space, you can also pick sample times, and then you get a somewhat weaker guarantee that says, well, you look at the underlying trajectory and you sample it exactly at the sample times, and you evaluate the LTL formula at the sample times. Okay, so let me continue. So essentially, what I've talked about is that I've talked about components of robots that do control computation, sensing, actuation, and messaging. And then we built on top of ROS and some real-time operating system. But if you want to create a large-scale robotics framework, this is only part of the story. There are many other things that you have to do before it becomes useful. For example, concurrency management, provisioning robots, failure recovery, managing the state of the, of the entire system, as well as things like lifelong task planning. So usually in many of these situations, there will be a continuous stream of concurrent requests that come to the system. And there's a task assignment and planning phase that has to decide how to take a task and give it to a robot. And finally, there's also the question of how you take user intent and translate it to a system. If you want end users to be using these robots, you cannot assume that they know all about linear temporal logic. Most linear temporal logic experts do not know a lot about linear temporal logic when it comes to expressing tasks. And I will very briefly talk about two projects that we have looked at in this world. So AntLab is essentially a project that tries to add this kind of software engineering infrastructure on top of these robot programs. And part of the research in AntLab is to look at different kinds of planning problems that come up in this lifelong planning situations. You have a robot that is already going to a certain target and a new task comes in. Will you interrupt the robot so that it just goes a little bit out of its way to tackle this task as well? Or do you give this task to a completely new robot? Or do you wait for this robot to finish its task and only then take a new one? So there are very nice planning problems that show up through this AntLab project. And the other project, this LTL little talk, is the one that I want to spend a little more time on. And this is essentially trying to get user intent through natural language and demonstrations. And we do this in a somewhat idealized setting where you have this gray robot in a world with different items with shapes and colors and different rooms and so on. And what we'd like to do, and let me just show you a demo of the system, is that we would like the user to be able to write down natural language requests, and these should be learned or understood by the system. So underneath the system, there is a certain stylized form of a linear temporal logic. So for example, you can say things like eventually pick one circle item at a certain location. But of course, the user may not know this particular syntax. They could just say get one circle item from some location. Now, if you get something like this that the system does not understand, what we do is we ask the user to show a demonstration in this world. Okay, so the user shows a trajectory of what happens, and then the user and then the system interactively asks the user for certain instances. Okay, so the system says, "Does this satisfy your constraint?" And the user can say yes or no. And essentially, the system disambiguates the particular property that was shown, and now the system essentially learns what the user intent was, right? And the user intent is essentially learned as a linear temporal logic specification. But moreover, just through some natural language processing tricks, the underlying system generalizes from what was learned. So what was learned was get one circle item from 7.4. But now the system, once it learns this, can also generalize to say that, well, if the user wants to get two triangles from some other location, then the robot knows exactly what to do. So this is essentially something that we are playing with now. We are taking an underlying LTL planner, and we are trying to connect it to end user programming given through demonstrations, learning, and disambiguation that is done interactively with the user. So this was roughly the last thing that I wanted to talk about. So we are almost towards the end of my talk. What I want to tell you is that I kind of presented as if there are all these nicely shaped bricks that fit together very well. The actual situation is more like this. We are making part progress in many of these domains, but there are still certain points at the interfaces where more work needs to be done. And this is really an area where there's really a lot of work to be done. So initially I showed you all these different fields and I kind of put them together. In practice, these fields are not really that close, and you have to do quite a bit of work in order to bridge this gap. And finally, I only talked about certain small problems in control design and programming abstractions and so on. There are, of course, many other problems in this domain that have to come into the formal foundations of robot programming. I mentioned a little bit of software engineering. There's also this entire area of simulation, testing, and verification. There's the human-robot interaction. There is the mechatronics and devices and sensors and so on. And there's, of course, the elephant in the room, machine learning and data. How do you make these formal foundations compatible with learning and data? I'm going to stop here. I just want to show that this is work that was done with many different colleagues and students. And at this point, I would like to stop and I would like to take your questions. Thank you very much for listening.
Thanks a lot, Rupak, for this amazing talk. You walked us through so many complex concepts with very clean slides and explanations. So I think it was really a wonderful talk. I see we already have a question by Rong again. Can you talk more about collision avoidance, verification of collision avoidance by using PGCD?
Yes. So the way we do this is the following. So remember, I told you that each of these motion primitives, each PGCD process comes with a footprint. And you can think of the footprint as essentially a constraint that tells you what is the geometric space that is used by an object. And the footprint is actually a function of time, because depending on the state of the system, the footprint may be different. An arm that is extended will have a different geometric footprint than if the arm is folded. So now when we look at this, the motion compatibility check, part of the motion compatibility check is to make sure that we take these footprints and we do essentially that their intersection is empty. Because the intersection essentially tells you, so for every time, the intersection of the footprint at that time between two components must be disjoint. You can formulate this as an SMT query because these footprints are usually given by some polynomial enclosures. And in general, to simplify the SMT's life, no approximation. So for example, for the Franca arm, the actual envelope is a rather complicated geometric shape, but most of the time we will essentially approximate it by a bunch of cylinders. Okay. So essentially, this is how we do the geometric collision check.
Thanks. So you already answered plenty of questions, but if you agree, we can probably take one more, and I'll let my co-chair Sergey ask it.
Yeah, so Rupak, there's also questions coming over Slack. So there's a question by Cheyenne, who says that one of the big advances in robotics in recent years is perception. Can you share your take on how perception can be folded into PGCD or one of the other layers in your framework?
That's an excellent question. And I had this slide made just for this question. Yes, this is a problem that we all know, right? So essentially, the perception stack is based on machine learning. And really, it is very difficult for us at this point to be able to give end-to-end formal guarantees if there is a machine learning box in the middle. And I wish I knew how to answer this question. Maybe in some years we figure out either interfaces between the more formal part and the perception part, so that we can give results modulo. So in the sense that we can give, if the perception part guarantees a certain behavior, we will be able to give an end-to-end thing, or maybe we give some kind of pack-like guarantees. But I really don't have anything better to say at this point. And of course, the other aspect would be that if one could have such systems that we don't understand or we cannot formally reason about, at the very least, can we try to get some consistency over time from these systems, or provide some kind of explanation on why a certain perception module thought that a certain scene looked a certain way. On the other hand, again, I don't really have a good idea of how to answer these questions at this point. But as well as I do, that this is essentially one of the directions that many of us are trying to look at.